Hello guys, welcome back to my channel. Today I have an integral with a lot of trigonometric functions and not only trigonometric functions but also inverse trigonometric functions. So in all it's a big uh, trigonometric extravaganza, so as to say. So let's get to it. So we have an integral as always, let's call it I, which goes from 0 to pi by 4, and integrand is inverse tangent of 2 times cos squared theta over 2 minus sine 2 theta times secant squared theta d theta. Now, looking at this secant squared theta d theta, if you have been practicing integration a lot, you might notice this to be the derivative of tan theta. So that's to say that if somehow we were to introduce a substitution, say u equals tan theta, then we would have du equals secant squared theta d theta, right? So we want to find a way to somehow make this substitution. And how will we ensure that we make this substitution useful? Well, that is if we can convert everything that's inside into in terms of tan theta. And this inverse tangent outside is actually a hint that this inverse tangent and this inner tan is somehow going to just cancel out or something, or I don't know. Let's just see. But what my intuition tells me is that this question wants us to introduce this substitution, because we have a secant squared theta d theta here, right? So let's just write everything that's inside the argument of this inverse tangent in terms of tan theta, so that we can make greater use of this substitution. Let's do that first. So we have the integral from 0 to pi over 4 of the inverse tangent of 2 cos squared theta over 2 minus. Now what is sine 2 theta? Well, we know the double angle formula for sine 2x. For example, we have 2 times sine x times cosine of x, but instead of x we have a theta here, right? So let's just implement this formula. Okay, instead of this sine 2 theta we have 2 sine theta times cosine of theta, and we still have the secant squared theta d theta outside. So we have the integral from 0 to pi over 4 of the inverse tangent, and we can just cut 2 from the numerator and the denominator. So we have cos squared theta over 1 minus sine theta cosine theta and secant squared theta d theta as it is. Now, as I said, we want to somehow make a substitution in the place of tan theta, right? So we need a tan theta inside this argument here. And the way we can do that is divide numerator and denominator by cosine squared theta. And you will see in a minute why I said why cosine squared theta, because yeah, let's see that. So if I divide the numerator by cosine squared theta, I'll just have a 1, and then 1 over cosine squared theta is a secant squared theta, and then I have a sine theta cosine theta divided by cosine squared theta, and the secant squared theta d theta as it is. Now the great part is one of these cosine thetas cancel, and what is a sine theta over cosine theta? That's right, it's a tan theta, right? And we can also rewrite this secant squared theta as 1 plus tan squared theta. That's just the square identity of trigonometric functions. And we have a negative tan theta here. And secant squared theta d theta. So as I said at the start of the video, we can definitely substitute tan theta for a single variable, because the derivative of tan theta, that is secant squared theta d theta, is just present outside, right? So we can proudly say that let u equals tan theta, because du is secant squared theta d theta. So this thing is du. Well, our integral I now becomes, okay, so when theta is 0, u is 0. When theta is pi by 4, tan of pi by 4 is 1. And we have an inverse tangent as it is. And 1 over 1 plus u squared minus u. And we have a du here. Now, what can we do here? Let's just factorize the u in the denominator. Integral from 0 to 1 of the inverse tangent of 1 over 1 plus u times u minus 1 du. Okay, we have this thing in the denominator, right? Well, what is a 1? 1 can be simply written as u minus u plus 1, right? I mean, the u's will eventually cancel out, we'll have a 1. Or you can say u minus 1 in a bracket, right? Just factorize out the negative sign. Well, let's just write that for the numerator for a minute. So integral from 0 to 1 of the inverse tangent of u minus 1 over 1 plus u times u minus 1 du. Now, I mean, this inverse tangent expression entirely is something exotic, so I'm going to do that on the next page. See you there. Well, so this is our integrand, right? The inverse tangent of u minus, in bracket, u minus 1 over 1 plus u times u minus 1, right? Now let me remind you of a formula from inverse trigonometric functions from ITF. Say if you had an angle tan inverse of A added with another angle, the tan inverse of B, for example, you simply obtain the inverse tangent of A plus B over 1 minus AB. Well, this was for a positive, right? What's for a negative? So we have the inverse tangent of A minus the inverse tangent of B, that equals the inverse tangent of A minus B over 1 plus A times B, right? Now let's look at the second formula. Well, looking at the second formula, we can compare this indeed with our integrand over here. Well, we had an A in the formula, and what do we have here? Well, this is our A, and what's our B? This thing is our B, and let's check if the denominators match. So we know our A, we know our B, and then 1 plus A times B, right, according to this formula. 1 plus A, which is our U, and B, which is our U minus 1. Yes, it matches. Perfect. We can just decompose our integrand into the inverse tangent of A minus the inverse tangent of B. So we know our A and B, so nothing else changes. We have integral from 0 to 1 of, instead of this thing that we just checked if this matched with our integrand, right? We can just decompose our integrand into tan inverse of A, and what's A? U, minus the inverse tangent of B, and what's B? U minus 1. And these two things are under one integral, du. Well, we can split them into two integrals by the linearity property. We have the inverse tangent of u du minus the integral from 0 to 1 of the inverse tangent of u minus 1 du, and I'm going to be calling this I1, I'm going to be calling this I2. So this is our I1, right? Now how can we integrate this inverse tangent? Well, you might know by experience, or if you are not so experienced, let me tell you now that we can only perform integration by parts on this thing. We can only perform integration by part because there's literally nothing we can do. We could try to do a trig substitution, but eventually we will just end up with theta, and I think a secant squared theta d theta, and then again we would, theta and some integrable function, we would again have to use integration by parts. So integration by parts is inevitable, anything you choose to do. So I won't like to introduce another substitution, so I'll just integrate by parts right now. So we don't know the integral of this, right? So this will be the function that we differentiate. So I'll call it d, and there's always a 1, this omnipresent 1, right? When we can integrate that, so that's I. It's a classic di method. So well, we integrate 1 both times, right? So integral of 1 with respect to u is u, and then we don't touch the second function, we don't touch d in the first part. Then minus, we again integrate 1, that's you're always going to do that, and then we multiply by the derivative of this tan inverse of u. What's the derivative of the tan inverse function? Well, it's 1 plus the argument squared, right? So 1 plus u squared, don't forget the du. And yeah, this is evaluated from 0 to 1, and this is an integral from 0 to 1. So let's plug in 1. So 1 times the tan inverse of 1 minus 0 times the tan inverse of 0 minus the integral from 0 to 1 of u du over 1 plus u squared. Now the tan inverse of 1 is pi by 4. Because of this 0, this thing will go to 0. We have minus. Now what's the derivative of the denominator? It's 2u, right? Because the 1 becomes a 0. And we have a u on top. So why don't we try to reconstruct the derivative of the denominator on top? We need a 2u for that. We need basically a 2, right? We have a u. So why don't we multiply and divide by 2? So we have half times 2u over 1 plus u squared du, evaluated from 0 to 1. And well, when we have the derivative of a function in the numerator and the function in the denominator, and we integrate that, we always obtain the natural log of 1 plus u squared, or whatever that function was. Here it's 1 plus u squared. We evaluate that from 0 to 1. We have pi by 4 minus half, and when u is 1, 1 squared is 1, 1 plus 1 is 2, so ln of 2, then minus minus becomes a plus, half ln of, when u is 0, 1 plus 0 is 1, and we know for a fact that the natural log of 1 is 0. So I1, for I1 we simply get pi over 4 minus half the natural log of 2. So okay, so for I2 we again have an inverse tangent, and again we are going to use integration by parts. I mean, we can't do anything over here. You can try, but you'll always have to resort to integration by parts. So let's first accept that you can't do anything, and then we can get ready for integration by parts. So we're going to be integrating 1 and differentiating this tan inverse of u minus 1. So the integral of 1 with respect to u is u. We don't touch the second function, u minus 1, evaluated from 0 to 1, minus, again we have a u, divided by 1 plus the argument squared, right? U minus 1 squared, and since the derivative of u minus 1 is 1, so we don't care about multiplying the coefficient due to some chain rule. That's a great thing. Again, integral goes from 0 to 1. Now we can plug in 1 here. 1 times the inverse tangent of 1 minus 1 is 0. Then minus 0 times the inverse tangent of negative 1 minus the integral from 0 to 1 of u du over, why don't we expand this thing, 1 plus u squared minus 2u plus 1, and this 1 makes it this thing 2. Fair enough. Well, the inverse tangent of 0 is 0, so this thing goes to 0. Because of this 0, this thing goes to 0. So we are only left with negative of this integral u du over u squared minus 2u plus 2. Why don't, like I1, why don't we try to reconstruct the derivative of the denominator in the numerator? So what's the derivative of the denominator? It's 2u minus 2, right? You can do it on a piece of paper if you don't agree. So 2u minus 2. So we need a 2u. So we'll multiply and divide by 2. Minus 2, right? So we need a minus 2 plus 2, because originally there was no 2. But then, just to maintain equality, we're going to have to add and subtract 2. So we can split it into two integrals. Minus half times the integral from 0 to 1 and 2u minus 2. So we match the derivative with the denominator. U squared minus 2u plus 2 du. We have a negative half, and just 2 du over u squared minus 2u plus 2. Integral goes from 0 to 1. I always keep forgetting that. Okay. Well, we matched the derivative of the denominator in the numerator. So we can directly use this natural log formula that we have. The natural log of u squared. Well, it's absolute value actually, because we don't know if it's positive or negative, and we always want a positive inside the natural log. So u squared minus 2u plus 2, evaluated from 0 to 1, minus, well, this 2 will certainly cancel out. We have integral from 0 to 1 of du over, well, can we complete the square and just simplify this identity a bit? So we have u minus 1 the whole squared plus 1. I completed the square, or you can just revert back to what we had initially. Right, and you'll see in a minute why. So let's just plug everything in. So we have minus half. Then when I plug in 1, I have 1 minus 2 plus 2. Minus minus make this plus, so plus half of the natural log of 0 minus 0 plus 2. And then this form of the integrand, we have a specific formula for this. I'll probably show you in another video why this is true, but for now this is just 1 over whatever is squared. So over here we have 1 squared, right? So whatever was squared, so 1 over that, so 1 over 1 times the inverse tangent of this variable that was squared. Can be any linear variable. So here it's u minus 1 over this number that was squared, so 1. Because if we had a 3, we would write this as a root 3, the whole thing squared, and then we would have 1 over root 3 times the inverse tangent of u minus 1 over root 3. So I hope I'm making sense there. And let's not forget our upper and lower bounds. So these 2's cancel out. Natural log of 1 is 0, so this thing goes to 0. We just have a half times the natural log of 2 here, and minus the inverse tangent of u minus 1 evaluated from 1 to 0. Let's finally plug in u equals 1. 1 minus 1 is 0, and then minus minus make it plus, so plus inverse tangent of, when I plug in 0, I have a negative 1 here. The inverse tangent of 0 is 0. The inverse tangent of negative 1 is negative pi by 4. And I have plus half the natural log of 2. That's precisely our I2. So what was our original integral I? It was I1 minus I2, right? If you remember the result of I1, we had pi over 4 minus half of the natural log of 2, and then minus I2. So I2 was negative half natural log of 2 plus pi by 4 because of this negative. So these natural log terms cancel out, and we have a pi by 4 plus a pi by 4. And if you know how to add fractions, that's 2 pi by 4, which is nothing but pi by 2. So I is precisely pi by 2. And now, just for the sake of just writing the question again, and giving you an entire perspective of what happened, because if someone asks you what was this video about, you should be confident to say that this integral from 0 to pi by 4 of the inverse tangent of 2 cosine squared theta over 2 minus sine 2 theta times secant squared theta d theta equals precisely pi over 2. You should be confident enough to say, if somebody asks you what was gamma digamma's new video about, you should be able to confidently say that this integral that we define to be I is precisely equal to pi by 2. So much for trigonometric extravaganza. I hope you like this video. Please click the like button, share, subscribe. Have a great day. You can always comment down and reach me if you have doubts or you want to discuss anything. Stay home, stay safe. Peace out.